Hello everybody. Welcome back to the International Seminar on Automorphic Forms. Today we have Haocheng Fan from the Peking University that will teach us about an algebro-geometric approach to the automatic convergence theorem for Shimura varieties. So, please, Haocheng.
Okay, thank you for Ricardo's introduction and invitation, and it's a great honor to give a talk here. Today I will talk about an algebro-geometric approach to the automatic convergence theory for Shimura varieties. In the first half part, I will talk about my thesis, which deal with the single modular variety case, and in the second half, I will talk about joint work in progress together with Peihang Wu and Jiacheng Xia to deal with general Shimura varieties. Okay, let's begin. So I will talk about the coherent cohomological dimension first. Assume that X is a quasi-projective variety over an algebraic closed field K, which is characteristic 0. The coherent cohomological dimension of X is defined as the maximal index I, such that HIXF is non-zero for some coherent shift F on X. Uh, hmm? Okay. And for example, if the CCD of X is 0, if and only if X is a affine variety, and the CCD of X is equal to the dimension of X, if and only if X is projected. And for general Shimura varieties, a conjecture made by my advisor Liang Xiao is that if Gx is a Shimura data and the adjoint group GAD is Q-simple, denoted by the Shimura KGX, the associated Shimura variety of level K, then the CCD of this Shimura variety is at most the dimension of minus the Q rank of the adjoint group GAD. And it's well known that the Shimura variety is projective if and only if the Q rank of GAD is 0, which means to check that GAD is isotropic or anisotropic. So the previous conjecture holds when the Q rank of GAD is 0 or 1. Because if it is 0, then dimension is equal to CCD, and if it is at least 1, then the CCD is at most the dimension minus 1. So the conjecture holds. And the interesting thing is that the property that CCD of the Shimura variety is at most 2 less than the dimension of the Shimura variety can be related to the what we call the automatic convergence theory. I will expand this automatic convergence theory later. We will focus on the single model variety AG gamma in the first part. The conjecture holds when G is at mode 4 by constructing some kind of affine stratification of the AG gamma. But there's no non-trivial results when G is at most 5, at least 5. Because we have a good description when G is at most 4. It's a moduli of some kinds of curves. Yeah, copy of curves, something like that. But for G is at least 5, we don't have a good description and not good description of the zero of model forms, something like that. And my theorem is that if G is at least 2, then the CCD of the single model variety AG gamma is at most the dimension minus 2. So it can be related to the automatic convergence theory. We will see. Let me recall the automatic convergence theory first. It's a theory in CUDA's program. Let V be a quadratic space over Q of signature N2, and L be an even lattice, L prime be a still lattice. This data and the level gamma define an orthogonal Shimura variety X gamma. And there is also a representation which is called a Wei representation. The space is the complex vector space of functions from L prime quotient L or G copies of L prime quotient L to C, and the metapletic group MP2GZ acts on it, and the representation is called the Wei representation. And for every positive semi-definite matrix T, which is Q coefficient and symmetric, and every phi in SLG, there's a special cycle class ZT phi in the Cho group, Cho G X gamma C. It's a codimension G Cho group with coefficient C. The formal generating series defined by Kula and Milson is that uh, it's the formal power series. Sigma G tau is uh, the sum of ZT and QT, whose coefficients lies in the dual representation of SLG tensor with the Cho group Cho G. And Kudla conjectures that the formal generating series sigma G is a modular form. The weight is 1 plus n half of n, and the representation is dual of the weight representation and valued in the Cho group. And in Wei Zhang's thesis, he proves that the formal generating series is a formal single modular form, which is also called a symmetric Fourier-Jacobi series. It should be a formal Fourier-Jacobi series, a symmetric formal Fourier-Jacobi series is a formal power series whose coefficients are single Jacobi forms phi m and of weight k index m, and m is a G prime times G prime matrix. Here the G prime is the G minus G prime is what we call the cogenus, and G is the genus. The space of this kind of formal power series is denoted by Fm K G G prime, and if it admits a representation, we write a row here. And Wei Zhang series states that the sigma G is lies in the formal model space of formal model forms of genus G and exactly cogenus 1 and weight 1 plus n quotient 2. Representation weight is the exact weight representation and valued in the Cho group of cogenus codimetric G. And in Brunier and Raum's paper, they proved that the automatic convergence theory, which says if G is at least 2 and G prime lies in between 1 and G minus 1, and rho is a finite dimension representation of MP2G with a finite index kernel, then the space of formal modular forms is equal to the space of modular forms. And that's what we call the automatic convergence theory, because a formal power series automatically converges. And this theorem can be reduced to the case G prime is 1 and rho is a trivial representation. And in this case, we can reinterpret this case in algebraic geometric language. That's what Brunier and Raum did in one of their another paper in 2024. Let AG gamma minimal be the minimal computation of AG gamma, and D gamma minimal be its boundary. And A hat gamma G gamma minimal be the formal completion of AG gamma minimal along the boundary. And omega hat be the pullback of the Hochuli bundle. We have the space of the formal model forms of genus G, cogenus 1, level gamma to be the is the global section of the omega hat K on this formal scheme. Then the above theorem can be written as H0 of the omega K equal to the H0 of the omega hat K. And this kind of equality appears in the classical condition, which is called Grothendieck-Lefschetz condition. For projective variety X over still over K and a closed subvariety Y, there's a Grothendieck-Lefschetz condition left XY, and a pair XY satisfies left XY if for every connected open neighborhood U of Y, and every fact bundle E on U, the restriction map from H0 U E to H0 of x hat at pullback of E is an isomorphism. In other words, every something like the global sections of the formal scheme can be extended to the open neighborhood of, of Y. And of course, it will is stronger than the equality here. And my theorem is that the pair of the minimal commutative and the boundary satisfy this kind of GL condition, the Grothendieck-Lefschetz condition. Uh, I want to make a remark here that the stratification of the boundary also satisfies the GL condition. And this corresponds to the cogenus G prime. In Bernier and Raum's theorem, they allow G prime to be any number in between 1 and G minus 1. And here we can also do a similar thing. When gamma is gamma 1, the boundary D gamma 1 minimal admits a stratification. It's a disjoint union of smaller genus single modular varieties. It's something like A0, A1, disjoint union of A0, A1 to AG minus 1. And we denote the D gamma 1 L to be the disjoint union of the A L prime with L prime less than L. And we denote that D gamma L minimal to be the sorry, to be the preimage of D gamma 1 L in AG gamma minimal. And then the statement is that the pair AG gamma minimal and D gamma minimal L also satisfies the Grothendieck-Lefschetz condition if L is at least 1. L is equal to the G minus G prime in Bernier and Raum theory. And another remark is that for toroidal commutations, the similar result is also true. If AG gamma sigma is the toroidal commutation and the D gamma L sigma be the preimage of D gamma L minimal, the pair of AG gamma sigma and the D gamma L sigma also satisfies the Grothendieck-Lefschetz condition if L is at least 1. And the relation between the left xy and the CCD is given by the following proposition. Assume that y intersects every effective divisor of x non-trivially. Here, non-trivial means that the intersection is not an empty set, and x is smooth. Then the following statements are equivalent. The first one is that the pair x and y satisfies the Grothendieck-Lefschetz condition. And the second one is the complement of y in x. It has CCD at most dimension of x minus 2. I also want to make a remark here. We have already seen that the Grothendieck-Lefschetz condition implies the automatic convergence theory in this case. And however, in another approach to the Kulas program by Wen Xuanqi, Lin Lishi, Liang Xiao, and Yichao Zhang, the second property, the CCD bond, appears naturally. If you were in CIRM, you my advice Liang Xiao give a talk about this approach. Now we need to expand the strategy we proved this. Also assume that y intersects every effective divisor of x non-trivially. Then we have another equivalent statement. If x and y satisfies the Grothendieck-Lefschetz condition left x, y, and then we will have y is weakly G3 with respect to an ample lie bundle L. These two are equivalent. And I want to point out that we don't need x to be smooth here, but we still need it to be normal. And Since the minimal codimension of proper subvarieties in AG gamma is at least G, so if G is at least 2, then every effective divisor of AG gamma minimal will hit the boundary. So our strategy to prove the previous two theorems is to show the boundary D gamma L minimal is weakly G3 with respect to the whole Lie bundle, which is ample in AG gamma minimal for L is at least 1 and G at least 2. I'll explain what is the weakly G3. Uh, Assume that X is a projective normal variety and Y is a connected closed subvariety. We denote X hat to be the formal completion of X along Y, and let M X hat to be the sheaf such that for every fine open U, the ring of M on U is the total ring of fractions of the structure sheaf on U. We denote by the Kx hat Y to be the closed sections of the sheaf Mx hat Y. Uh, it will be a field if X is a projective normal variety and Y is a connected closed subvariety. And there will be a nature embedding alpha xy from the rational field kxy to kx hat y. And for a fixed Lie bundle L on X, we denote by the L hat to be the pullback of L on X hat. We can define two subfields kxl and kx hat L hat to be the quotient of global sections of the power of L and L hat. And the definition of G2 and G3 is we say Y is G2 in X if the field Kx hat is a finite field extension over Kx. So, if you have nature embedding X alpha X Y. And we see that Y is G3 in X if these two fields are equal. And we see that Y is weakly G2 with respect to L if a similar result holds for the subfield given by L. Which is weakly G2 if Kx hat L hat is a finite field extension over the field Kxl, still given by alpha xy, and the rational field Kx is equal to the field Kxl. When L is ample, this equality holds naturally. And we see that Y is weakly G3 with respect to L if these three fields are all equal. Um, we need two key properties of the field K hat X over Y. The first one is that assume that F is a proper surjective morphism between irreducible varieties. Then for any closed subvariety Y of X, there is a canonical isomorphism. Uh, the left-hand side is the field of the formal rational functions of X prime and F infers the preimage of Y in X prime. And the right-hand side is the tensor product of the formal rational fields Kx hat and Kx prime. And here the zero means that the ring of the total ring of the fractions. And the corollary is that if the F is a morphism given by a group quotient of a finite group that acts faithfully on X prime, and we know that both fields K X prime hat F pullback of L hat and K X hat L hat are fields, then we have something looks like a base change theory. The mm, the field of formal rational functions is exactly the field of formal rational functions tensor with the rational functions, field of rational functions. Another important properties given by the Batzu and Schneider is this that uh, if there is a finite field extension of kx in kx hat given by denoted by k prime, let f be the normalization of x in k prime. Then there exists a closed embedding I prime, which lifts the inclusion embedding I from y to x. And the morphism f is itself in a neighborhood of I prime y. And in particular, uh, the uh, the image I prime y will be a connected component of the preimage of y by f. Okay, now we are ready to sketch the proof of the theory about the weakly G3. We sketch the proof 1L is G minus 1, which is the same as the G prime is 1. We still let A hat G gamma minimal denote the formal completion of A G gamma minimal along the whole boundary. The first step is that we need to show that uh, there exists a degree equal to the dimension G times G plus 1 over 2 polynomial P, such that the dimension of the globe sections of omega hat K is at most is controlled by the polynomial P, controlled by PK. This implies that the boundary D gamma minimal is weakly G2 with respect to omega. In other words, the the Ka hat omega hat is a finite extension over the field Kag gamma minimal. The second step is that to take the normalization of Ag gamma minimal in the field Ka hat omega hat. And then by the second key property, we have a embedding F prime from the gamma minimal to B gamma minimal, which lifts the embedding I. And the image of I prime D gamma minimal is a connected component of the preimage of gamma of F gamma of the gamma minimal by F gamma. We also denote the preimage of the zygomodal variety Ag gamma by B gamma, and let delta gamma prime be the ramification locus of F gamma in B gamma. And we denote by the delta gamma, denoted by delta gamma, the image of the delta prime gamma. Delta prime gamma is the ramification of this map, and the delta gamma is the image of delta prime gamma. The third step is a key step. We show that the delta gamma is stable on the hack actions. More precisely, for hack correspondence given by uh, given by x, we have three Cartesian squares. The left arrow is is given by is given by the inclusion of the level gamma and gamma prime, and the right hand side is given by the inclusion of the level gamma and x gamma prime x in first, and this arrow is given by times x. This is an isomorphism. And by the first key property, we know that the function field of B gamma prime is the tensor product of the function field of B gamma and the AG gamma prime over the function field of AG gamma. And the normalization is commutes with the commutes with the smooth morph base changes. And pi 1 if gamma is neat, pi one is a Italian morphism. So least square is Cartesian, and least square similarly least square is also Cartesian, and this is x is a isomorphism, so this is a Cartesian square. Um, we have these three Cartesian squares, then the ramification locus should be hx of delta gamma, uh, which is the preimage of delta gamma by pi 1 and take the image of this preimage to AG gamma again, then it should be lies in the delta gamma. So therefore, delta gamma is stable on the hack actions. But however, if delta gamma is not empty, then any C point of delta gamma will generate something like a hack orbit. But every hack orbit is directly dense. But delta gamma is not directly dense. It has to be contained in at most a codimension one closed subset. So it has to be empty, and F gamma should be finite tau in B gamma. And the final step is that the results on the congruence suburb problem for SP2G implies that the finite morphism of finite cover of AG gamma has to be uh, another single model variety AG gamma 0. So B gamma is equal to AG gamma 0 for some gamma 0. And in particular, the boundary of the B gamma minimal has to be connected. So it has to be the I prime of D gamma minimal, because we know that I prime D gamma minimal is a connected component of the preimage of D gamma. So we can conclude that the morphism F gamma sends B gamma to A gamma and sends I prime D gamma minimal to D gamma minimal, and is an isomorphism on the boundary. And it is finite tau on B gamma and the open neighborhood of I prime D gamma minimal. So F gamma is finite tau and is an isomorphism on the preimage of D gamma minimal. So it has to be an isomorphism. And now that's a proof of the weakly G3 property, weak G3 property for the single case. Uh, okay, and then let's move to the general case. We have already seen that the theorem for coherent cohomological dimension and the Grothendieck-Lefschetz condition and the weak G2 and G3 properties hold for general varieties. And now we list the inputs from the single model variety. The first one is that the minimal computation of the single model variety is normal and its boundary is connected. This implies that the field the ring of formal rational functions is a field. The second one is that every effective divisor in AG gamma minimal intersects the boundary non-trivially. This implies that the weak G3 property is equivalent to the Grothendieck-Lefschetz condition, and the coherent cohomological dimension bound. The third one is that we need the existence of asymptotic bound. The dimension of the H0 of the omega hat k power is controlled by a polynomial p. And this implies that the boundary is weakly G2 with respect to the Hodge-Lie bundle in step 1. And finally, we need that every finite integral cover of AG gamma is still a connected Shimura variety AG gamma prime. This implies that B gamma has to be a single model variety. So B gamma minimal has will has connected boundary in step 4. And so um, that implies that the boundary had to be the lift of the image of the lift I prime. Uh, I will claim that we will have a good generalization for above inputs in general Shimura case that we expected, except for the third one, the polynomial control. This is exactly the algebraicity of formal forms. Um, um, to state our generalization, uh, we need to introduce the connected Shimura variety. The dimension is that a connected Shimura datum is a pair Gx plus consisting of the semi-simple algebraic groups over Q and GAD G adjoint R plus here plus means the connecting component conjugacy class of homomorphism from S to GADR that satisfy the following three conditions. Uh, it's similar to the definition of Shimura data, but we need at G to be same simple. And remark is that for Shimura data Gx, and let x plus to be a connected component of x, then it gives then it gives a gr plus conjugate class of homomorphism from third table from S to G adjoint R. Then the derivative group G dir x plus is a connected Shimura data. For connected Shimura data Gx plus x plus, it will give a connected Shimura variety relative to Gx plus. It's which is denoted by d gamma, whose complex points is the quotient of x plus by gamma, where gamma is an arithmetic subgroup of GADQ plus, containing the image of a congruent subgroup of GQ plus. And remark here is that the connecting components of Shimura variety at Shimura K, Gx are all connected Shimura varieties relative to the associated connected Shimura data G dir X plus. So to compute the CCD of the whole Shimura data, you only need to compute the CCD of the associated connected Shimura variety. Now we can state our geometrical results. We assume that Gx is a Shimura data that G dir is Q simple and simply connected. Uh, we can always we can always find a simply connected the how to say it? For if G dir is not simply connected, we can find another Shimura data G prime X prime that G prime dir is simply connected and the joint group of G and the is equal to the joint group of G prime. So this condition is harmless. And we assume that the Q rank of G dir is at least 2. The Q rank of G dir is equal to the Q rank of GAD. I think it's well known from now on. That's the case what we expect to have the property of CCD bound or automatic convergence theory. Let G dir X plus be the associated connected Shimura data, and D gamma be an associated connected Shimura variety. Let D gamma minimal be the minimal convertication. Mm. Uh, the geometric results of my my our sorry, the geometric result is the first one. The gamma minimal is normal and its boundary is connected. The second one is that every finite integral cover of d gamma is a connected Shimura variety d gamma prime. And the third one is that if there is a finite morphism from a product of two connected components of some non-complete Shimura varieties, uh, you can also feel it. You can also say two connected Shimura varieties, which is non-complete. Then the minimal codimension of complete subvariety in Shimura KGX is at least 2. And in other words, every every divisor of the compactification of Shimura KGX will hit boundary, will hit the boundary. Now, the only rest thing is the algebraicity of the formal forms. Let D denote the boundary of the Shimura minimal compactification of the Shimura variety. We will need a we will need the asymptotic bound H0 of the completion of Shimura variety and the pullback of the Haocheng bundle K power. Sorry, missed the dimension here. Its dimension is less than constant C times K power to the D's dimension. We need this control to show the algebraicity of formal forms or the weak G2 properties in our sense. And we also proved that this space of the double sections of formal schemes and pullback of shifts can be identified as the space of the collections of compatible symmetric Fourier Jacobi series on each strata in D. Uh, in general, D also has a stratification, just like what I did in uh, a single case. Uh, and if this Shimura variety is the Hilbert single modular variety or unitary Shimura variety and level is 1, then the global space of the global sections in this sense is the same as the analytically defined space of symmetric Fourier Jacobi series. And this asymptotic bound has been proved in single case by Bruni and Rom in about 2015. And class, class number 1 unitary case of signature GG by Jiacheng Xia. And in general CM unitary case of signature GG by Rom just a few months ago. And we can now follow the idea in Rom's paper to prove that in Hilbert-Siegel case, uh, the asymptotic bound is also true. And we expect that this idea or this method can be generalized to some other cases like unit cases with mixed signature. Okay, so our main theory is that if there is this finite morphism from a product of two connected Shimura varieties, which are non-complete, and the asymptotic bound holds, then the boundary of the minimal computation of the Shimura variety satisfy the Grothendieck-Lefschetz condition, and the CCD of this Shimura variety is at most dimension -2. And the core is that for Hilbert's single modular variety, the assumption is true, so the automatic convergence theory holds. Uh, I think I will stop here. Thank you.